Hey guys, and welcome back to the Micro Tutoring channel. This is your host Chris for today, and in this lesson we'll be looking at forms of quadratic functions. By the end of this lesson, students should be able to identify forms of quadratic functions, convert between standard, factorized, and vertex form, interpret key features of each form, select the most useful form in a given context, and more. As this video will be in a question and answer format, I encourage you to pause the video, do your own answers first, and then use mine as an example, or just somewhere to gauge where you can see improvements from. Now, let's move on with the rest of the video. Section A, identifying forms. Question 1, state which form of each quadratic is written in standard, factorized, or vertex form. This video, or this little section here, is going to be a bit of revision on what we did last time. So, here, I want you to look at what each one of them looks like. And notice if you can get it into an ABC format, which is the standard form, a factorized form, which will have two separate polynomials multiplying by each other, or vertex form, where polynomial is squared, and then a number is added afterwards. Now, let's look at the first one. The first one can mirror up to that ABC form, making it a standard form. Second one, we see two polynomials multiplied by each other, which makes this the factorized form. C, we have a polynomial squared plus another number. This means it is the vertex form. And similarly, we see the same thing with D, which also makes it the vertex form. Now let's move on. Question 2. Can you remember what the standard form, factorized form, and the vertex form actually looks like? So if we quickly just go back to our previous slide here, just to use it as some help and some patterns, look at what again is standard, factorized, and vertex. This will help you greatly for standard, factorized, and vertex forms in its general forms with, random coefficients multiplying by x. So, standard form. Here we have, of course, the ABC form. ax squared plus bx plus c. A factorized form, we have y equals a times x minus r times x minus s. In vertex form, of course, we have y equals a times x minus h squared plus k. Now, another thing to notice, again, to remember, is that all these forms will have the a coefficient. And the a coefficient, if you remember, is just the coefficient that is going to be in front of here, the x squared, all the time. So it doesn't matter it doesn't matter how we expand it, it is always going to be a x squared. And when we put it in factorized form, we have to take it out, and same thing with vertex form. So we can put it cleanly in polynomials where x does not have a coefficient, like we see in the factorized form. We have the coefficient instead outside of the brackets, and the same thing with the vertex form. Now, let's move on. Section B, interpreting each form. Question 3. For the function y is equal to x squared minus 5x plus c, what is the value of c? C, and state the y-intercept. Now, here, if we look at this function kind of mirrors the ax squared plus bx plus c form. See, my C is a little bit wonky. So, because we are asked to find c, we can also simply just know that we're going to have our function in the standard form. And because our function is already given to us in the standard form, the a, b, c form, we can already see and match this 6 to the c here. Because remember, c is not a coefficient of any x, being x or x squared, like a and b are. Now, this means that, of course, the value of c is 6. And now, if you remember in our last video, our y-intercept, once we were making x equal to 0 to find the y-intercept, we would get a general form for the coordinate being 0, comma, c. Now, because of this, we already know what c is. So, when we state the y-intercept, we already know the coordinate is going to be 0, comma, 6. Remember, the x is first, and then the y is second for coordinates. Moving on. Question 14. For the function y is equal to x minus 2 times x minus 5, state the x-intercepts. Now, let's first do this the longer way, or I will show you exactly how to do this properly. So, to get the x-intercepts, we need to make y equal to 0. So this function would end up being something like this once we make y equals 0. So it will be x minus 2 times x minus 5 is equal to 0. Now to find the x-intercepts, or the x-coordinate of the x-intercepts, we need to follow the null factor law. And what we can do is because it's the null factor law, what we can do is when we look at these polynomials, we can actually break them on its own and make them equal to 0 on their own. And why can we do this? Because if one of these polynomials is equal to 0, well, then because of multiplication, the whole thing is going to equal to 0. So we need to find for what x value is going to make these two polynomials, or the whole function, equal to 0. So what we're going to have to do now is separate them out. So we have 0 equal x minus 2 and 0 equal x minus 5. Excuse me. Now, if we move the negative 2 to the other side, well, we would get 2 equal x. And similarly for the function to our right, the linear equation to our right over here, once we move 5 to the other side, we get 5 equal x, negative 5 to the other side. Now, what does this mean? This means that our x-intercepts are going to be 2, 0, and 5, 0. Now, once you get better at this, or once you do more and more of these types of questions, you can easily see that when you have them in factorized form, you can quickly look at these numbers here, and you know that the x position of the x-intercept is always going to be the opposite sign of that number within the brackets. Now let's move on to B. Explain what these values represent on the graph. Now, simply put, they represent points on the x-axis at which the parabola goes from positive y values or to negative y values. So the y numbers, the y values, go from positive to negative or negative to positive. And we can illustrate this if, sorry, let me just erase some of this working out. If we draw or just sketch the graph of the function. So if we were to sketch it, and when you do sketch, always remember to have labeled the axes. So if we were to sketch the parabola with our intercepts here, we're going to end up with something. We're going to end up where if we follow along the graph as we increase the x values, so we go down the graph here, as we cross the first x-intercept here, the y values go from positive to negative. And then once we cross the next x-axis, as we increase the x values, we move along the graph, the y values go from negative to positive. Now, let's move on. Question 5. For the function y is equal to x minus 3 squared minus 4, state the coordinates of the vertex. State whether the graph has a maximum or a minimum, and explain how do you know. Now, if we look at this graph here, we can see that it's in a vertex form. And because we're at the vertex, we have to make sure that the graph is always, or function is going to be in a vertex form. And remember, the vertex form is always going to look something like this. Now, state the coordinates of the vertex. In a general form, the vertex, especially once we get into the vertex form, is always going to be h, comma, k. Now, if we look to our function to the left here, we know that h is equal to 3 and not negative 3, because notice in the standard form it is a minus h, but because in the standard form k is a plus, we can say that in this case, for a function to the left, k is equal to negative 4. This makes the coordinates of the vertex to be 3, negative 4. And state whether the graph has a maximum or a minimum point. This graph will have a minimum point. So we explain how we know, because the a value, or the a coefficient here, over here, remember, is positive. In this case, a is 1. This means that the vertex here is a minimum, because remember, when we have a positive a coefficient, we're going to have a happy parabola. And because we have a happy parabola, we have a minimum vertex down here. Now, let's move on. Section C, converting between forms. Convert the following into a factorized form. Y equals x squared minus 7x plus 10. Now, to convert it in factorized form, which, remember, is going to be something like this, We can assume, by the way, that there's going to be no x coefficient out of this factorized form because there is none here. So I will write the factorized form now without an a coefficient. X minus r times x s. Now, once we look at what we have here, if we just simply look at what we're going to have, we're going to realize that once we do polynomial expansion, our standard form from the factorized form is going to resemble something like this. And let's quickly introduce what polynomial expansion looks like as well. So, polynomial expansion, we will start with the first term from the first polynomial and multiply that by all the terms within the second polynomial. So we have x times x, x times x, plus x times minus x minus s times x, plus, now we're going to get the second term from the first polynomial and multiply that by all the terms within the second polynomial. So now we have negative r times x, negative r times x, plus, sorry if this actually goes onto a second line, but negative r times s. So negative r, sorry, times negative s. So if we write this in a bit more of a clean form, we get x squared plus, sorry, minus, because remember we have a minus s up here, we have minus x sx, excuse me, minus sx minus rx plus, because two negatives make a positive, plus rs. Now we can also look at what we have here. We notice that we can take an x out. So we can factorize that as well into a minus x with an s plus an r, because remember, once we expand that here, we are going to multiply the first term because we only have one x. We only multiply x by everything in the second term, and it's going to be a negative x, so everything is going to be negative, and we're going to just get what we have up here. So this here also stays as r s as well. Now, what does this mean for us? Well, now we can look at what we have here, and we can relate this back to our original function over here. So, if I just remove some of this for a second, just leave us with what we want here in the corner, which is going to be an alternative version of the standard form. Well, now we can look at how can we get certain coefficients or certain values. So when we look at our graph here, because again we have an a coefficient equal to 1, we can already see that we have x squared, right? So this here is going to be the same as this down here. Now, we look at our standard form here, we're going to have a minus 7x. So we're going to have, if we just move out an x, negative x here, we're going to have something s plus r. So the s plus r is going to have to equal to 7. Right? It's going to have to equal to 7. So, if we just keep that there, s plus r is going to have to equal to 7. Now, similarly, we can also look at this here, and we can notice that it's going to be equal, 10 is going to be equal to r times s. Now, what we can do to make this a little simpler is break it down into some certain columns. So, we want to look at 10 and see all the different types of ways we can start off with whole numbers that we can get to multiply to 10 and see if any of those two whole numbers is going to give us a sum of 7. Because remember, we just have r and s. So, we can have 2 times 5 or 1 times 10. And both of them are going to be multiplying equal to 10. Now, let's look at these individual numbers. 2 and 5 and 1, 10. And let's sum them together to see what happens. So 2 plus 5 is already going to give us 7. So that means our r and s value are going to be 2 or 5. Now, let's just check 1 and 10 just to make sure that this also isn't another possibility. So 1 plus 10 is going to be equal to 11. So yes, S and R being 1 and 10 is not good or is not possible for what we want. So, if we go back now and remember the 2 and 5, if we go back now to a factorized form, which is going to be something like this, we can assign 2 and 5 to s and r. Now, it doesn't really matter if you assign 2 to r or 2 to s, but you'll have to make sure that if r is 2, then s has to be 5, and if r is 5, then s has to be 2. So, once we do that, and we assign, let's say, r equal 2 and s equal 5, we're going to get y equals x minus 2 times x minus 5, giving us our factorized form. Now, let's move on. Question 7. Convert the following into standard form. Now, if you remember what we did last time, where we did a polynomial expansion, we're going to have to do the same thing here to convert this factorized form. We can see two different polynomials multiplying by each other and get that into our standard form. Now, let's look at what we can do here. Now, remember, first term of the polynomial is going to multiply by all the terms within the second one. So here we have x times x, y is going to be x times x, and we're going to have now x times, sorry, not x times x again. We're going to have x times 1, so we're going to have plus x times 1. And now we take the second term of the first polynomial and multiply that by all the terms within the second polynomial. And another tip, if we were to have more than more than 2 terms within the first polynomial, we just keep going to every single term as so until we have no more terms within the first polynomial. Now, we will do -3 times x plus -3 times x, and then -3 times 1 plus 1 times -3. Now, if we simplify this a little, okay, x squared plus x minus 3x minus 3, and if we simplify this a little more through addition, we get x squared minus 2x minus 3. Now let's move on. Question 8. Convert the following into vertex form. Now vertex form, remember, is going to be something like this. We're going to have a squared polynomial. And to get that, we're going to have to do something called completing the square. But before we do completing the square, we have to make sure we factorize any type of a coefficient first. But if we look here at our function, we can already notice that our a coefficient is just going to be 1, so we don't really have to do any factorizing at all. So let's just get this started then. So because this is in a standard form, we can look at what we have here, and we're going to have to use something with, do something with our b. It's going to be a very interesting trick to get us a squared value. So look at our b, which is -4. Again, remember our standard general form for the standard definition. So b is going to equal to 4. And what we're going to have to do is we're going to have to use a little formula here. We go b divided by 2 squared. So we do b divided by 2 squared. We're going to have -4 divided by 2 squared. It's going to be equal to -2 squared, which is going to equal to 4. Now, what we're going to have to do is we're going to have to somehow get that 4 into our respective value. We're going to have to get that 4 into our quadratic equation. Now, we can't just add a 4 onto the end of our quadratic equation, but what we can is we can add a 4 and subtract a 4 simultaneously without simplifying. And I'll show you what that looks like. So we have y equals x squared minus 4x plus 4 minus 4 plus 1. Because if we were just to simplify what we have here, 4 minus 4 is just going to be equal to 0. So we're just going to get the same thing back. Now, I want you to trust my little process here, and you'll understand what this is going to look like a little bit towards the end of this question. So, we're going to have to simply bracket this off away from the minus 4 plus 1. Why? Because we're going to have to factorize x squared minus 4x plus 4. And to do that, we're going to have to look at our factorized form again. So if I erase some of that off and we write back what we need, we can have y equals x squared minus 4x plus 4, and then we can have a minus 4 plus 1 on the outside. This is just to give us a little bit more space. And if you want, we can simplify this part here at the end. So we have y equals x squared minus 4x plus 4 minus 3. Now, to get a squared value, we're going to have to, again, like I said, go back to this factorized form. And if we remember that little factorized trick that I did earlier, we're going to have to, where we expanded the factorized form, we're going to have to look at our little helpful formula here. We're going to have to see what values of r and s can we use to get our little squared polynomial. And just the tip here, r and s are actually going to have to be exactly the same. They're going to have to be equal to each other in this case to get a squared form, because we have to get two polynomials that look exactly like each other. First, let's go back and let's see what products or what terms can we multiply together. What numbers can we multiply together to get 4? So if we write down our 4 here, we can have 1 times 4. 1 times 4. 1 times 4. And we can have 2 times 2. And again, what can we have so that we take those numbers, and what can we have so that they also add up to 4? So, the first one, 1 plus 4, is not going to be equal to 4. It's going to be equal to 5. Second one, 2 plus 2 is going to be equal to 4. And what we can do as well, we can also double check that we have two values that are exactly the same, 2 and 2. So, if we keep that in mind, we have, and we erase some of this here, we erase some of this here, we're going to have r equal to and s equal 2. So, if we remember the factorized form, we're going to not include the a coefficient, because as we know, the a coefficient is 1. It's not really going to do anything. So, x minus r and x minus s we're going to have to now substitute that into here, x minus 2, the two s and r values, and x minus 2 again. So if we go to the left here and we write that out, we have x minus 2 times x minus 2 minus 3. And because those two polynomials are the same, we can simplify that to x minus 2 squared minus 3. Now, let me quickly show you another trick here that's going to help you make this process a little bit faster for you. So, let's remove all of this, because we can actually skip over this step entirely. So, if we go back to our B formula to get what we need for B, we can already predict what the H value, so H value in our vertex form, we can already predict what this value is going to be based on some calculations from the V. Now, if we go to y equals, sorry, the little b thing that we had to do earlier, where we had b divided by 2 squared. Now, what we can do is simply look at whatever we have in the b, divided by 2, and we notice, so in our case it was negative 4 divided by 2, which is equal to negative 2. That number, whatever number we get, is going to be equal to whatever number we have here, minus 2. So, to get the numbers that we have to add and minus, using our b from the standard form, we can kind of already skip to the vertex form by looking at what number we get before we square, just by simply looking at the b minus 2 section. And now, of course, I do want to warn you that minus 2 is not going to be equal to h, because if we look at the vertex form, that is minus h. But that minus 2 is just going to be put over here. And in this case, it works pretty well. But I also do want you to remember something, that you still have to do this full calculation with the b divided by 2 squared, so we can get, again, these values that are added and subtracted, especially the subtracted one. Because if we forget to do that, we're going to get a wrong answer. We're going to have plus 1 on the end here, which is not good. We want a negative 3, and we get that through the b divided by 2 squared. However, b divided by 2, whatever value we can get, we can kind of make a new general form where instead of a minus h, we can do something like a new general form for the completing the square component to make it a little bit easier for ourselves. Now, let's move on. Section D, matching forms. Question 9, the same quadratic is written in 3 different forms: x squared minus 4x plus 3, x minus 1 times x minus 3, x minus 2 squared minus 1. Explain what information each form reveals about the graph. First, we have the standard form. This helps us find the y-intercept, because if we remember, we can just simply, get it from C, because to get the y-intercept, x is equal to 0, and then we just see that we just get C for our y-intercept, or the y component of our y-intercept coordinate. The second is the factorized form, which helps us get the x-intercepts. Remember, null factor law. And the last one is the vertex form, which will just help us find the min or max point, which is also known as the vertex. Let's move on. Section E, application. Question 10. A quadratic has roots at x equals 2 and x equals 6. Now, roots also mean what are the x-intercept. So, when we see this, what are x-intercepts? Sorry, my spelling is a little bit off, but these are the x. Or more clearly, it gives us the x component of our x-intercepts, coordinates. Now, write the function in a factorized form. This is actually going to be pretty easy, because if you remember, we can get this from x minus r x minus s. This is what the factorized form is going to look like. And in this case, because we aren't given any information about the a value, we're going to assume that the a coefficient is 1, so we can just remove that. We can just erase that completely. And now, what are the roots? So, take a bit of a longer explanation. We can apply the null factor law again. So, erase that. Y equals to, we have to make y equal to 0 first. So, 0 is equal to x minus r x minus s. So, now, I'm going to have to move this to the left now. So, remember, in null factor law, if we look at our polynomials, because they are multiplying each other, if one of them equals 0, for whatever x value we get that to equal 0, then the whole thing is going to equal to 0, and it's going to equal to the left-hand side. So we can split the two polynomials up. We can have 0 equal x minus r, and 0 equal x minus s. And for both of these, we're going to get x is equal to r, or x is equal to s. And now, because we already know x is equal to 2 or x is equal to 6 for when y is equal to 0, we can already apply those numbers, 2 and 6, to r and s. And this will happen all the time. So, if we erase everything here, the factorized form is going to be equal to x minus 2 times x minus 6. Now, let's expand this into factorized form. I'm going to go a little bit quicker now, But we're going to still have to do some polynomial expansion. So x times x, x times -6, so plus -6 times x, and then plus -2 times x, plus, again, I'm going to go off the line a little bit here, but -2 times -16. If we simplify this a little bit, we get x squared minus minus 8x plus 12, because remember, two negatives will cancel each other out and will give you a positive when multiplying. Now let's move on. Question 11. A quadratic has a vertex of 3, -5 and opens upwards. Write the function in vertex form and expand to standard form. Now, opening up upwards gives us a very important clue. Because it opens up upwards, we know that the a coefficient is going to be a positive. And because it's the only information we get, we're going to assume that it's going to be 1 or -1, but because it's positive, it's going to be 1. And why? Because when the a coefficient is positive, it's going to give us a happy parabola that opens up upwards. Right? So, now let's write the function in a vertex form. So, y is going to be equal to, and again, a vertex form, this here is going to be equal to h, and this is going to be equal to k. So it's going to be x minus 3 squared minus 5. And let's expand this to standard form. Again, we can imagine this as x minus 3 times x minus 3 minus 5. We're going to go a little bit faster here to x minus 6, x plus 9 minus 5, which is going to be equal to y, x squared, minus 6x plus 4. Now let's move on. Question 12. Explain why different forms of a quadratic graph represent the same graph. Well, simply put, they are algebraically equivalent, meaning that the relationship between the x and the y, wrong y, I do apologize. So we're just going to get rid of this. And this means that for whatever x value we substitute, we will get the same y value result. So this means that if we were to put a 1, for example, into a standard form, substituting it for x, and y gives us 5, well then even if we put it in a vertex form or in a factorized form, it will still give us y is equal to 5. Now let's move on. Question 13. A student says a vertex form is not always the best form, and explain why this statement is not true. Sorry, vertex is always the best form. Vertex form can be good for determining the coordinates of the min or max point or the vertex just easily by observing the h and the k. However, if you want, for instance, to find the y-intercept or the x-intercepts of the graph, Instead, you want to use a standard and factorized forms, respectively. Let's move on. Question 14. In one or two sentences, explain when you would choose A, factorized form, and B, vertex form. Now, this is similar to our last question, but vertex for factorized form, this is when you want to easily express or identify x-axis intercepts within the quadratic equation. For B, vertex form, this is when you want to easily express or identify the min or max points. So factorized forms, x-axis intercepts, and vertex form, min or max points. And a bonus answer, you can actually use both to broaden your whole horizon of the graph and understanding of it, and it will help you graph it much more easily when you want to include all the intercepts and vertices. Except you would need to put it in standardized form or solve for that to get the y-intercept. Let's move on to our final question. In section H, check your understanding. Here we have x minus 4 squared minus 9. We need to convert that to factorized form, state the x-intercepts, and explain how the vertex relates to the x-intercepts. Each quadratic form reveals a different information about the same graph. So, for this part A, I am going to show you a neat little trick that's going to help you out a ton. So, let's write it out. First, let's actually solve for the different x values to find the x-intercepts. This is going to be a little weird, but it's going to help you understand the whole process of converting a vertex form into a factorized form. So first, we're kind of going to do B first. And when we got to do B, we got to let y equal 0. Y or 0 equal y. So we're going to have 0 equals x minus 4 squared minus 9. Now, to solve for this, we're going to have to move the negative 9 to the left to get 9 equals x minus 4 squared. And now, to get rid of the squared on the right side so we know what we want, we're going to have to, to get the x by itself, we're going to have to root both sides. We're going to have to root 9, and that's going to have to equal to x minus 4 when we cancel that. Now, when we're rooting 9, there's one thing we have to make sure we notice. Because when we root 9, we can easily just say that it's going to be equal to 3, because 3 squared is equal to 9. But isn't negative 3 squared also equal to 9? Well, yes. And because the 9 didn't have a square on the outside like the polynomial here, we can't simply just cancel out a square. And remember, because the polynomial on the right-hand side is squared to begin with, we are simply just canceling out the squared, and we're not going to have to do what we're going to have to do with 9. So on the root 9, I want you to also remember that it's going to have to be plus or minus 9, root 9. That's going to be the biggest takeaway here, because when we root it, it has to be plus or minus root 9. Another thing to notice as well, this wouldn't be possible if instead we had a plus 9 here, because when we move that plus 9 to the other side, it's going to give us a negative 9, and we cannot root a negative number at this moment in time unless you decide to do imaginary numbers later on. But if the 9 was a plus 9 instead of a negative 9, so if k is negative, sorry, if k is positive, then we cannot do this trick. Now, let's just erase some of this to get some working out space to find our x. So let's section this off here. We're going to move a little bit up here. So we're going to have two different processes in finding our x roots. So on this side, we're going to go with negative, and on the other side, we're going to have positive. So here, we're going to have root 9 positive. We're going to have 3 equals x minus 4. And on the other side, we're going to have negative 3 equals x minus 4. And as we move negative 4 to the other side, it's going to be here 3 plus 4 equals x. On the other side, it's going to be negative 3 plus 4 equals x. So x is equal to 7, and x is equal to 1. So these are the x roots. And if you remember previously from our x roots, we can simply just use them to, of course, get that into a factorized form. And because there's no a coefficient out here, this is just going to be a simple substitute. So we're going to have to assign one of these values, z, and 1. We're going to have to assign them to r and s. So we can get it into that factorized form. Let's quickly erase some of this out here so we can illustrate what we want. And so here, if we quickly just write out the factorized form again to jog our memory without the coefficient, we're going to have y equals, let's just let r equal 7 and s equal 1. We're going to have x minus 7 times x minus 1, giving us our factorized form. Now, I'm also going to show you something a little bit easier just to save us some time instead of finding, of course, the x-intercepts or the x roots along with our steps to find the factorized form. I'm going to show you something a lot simpler. So, remember this, keep this in mind. Keep this in mind as we simply go back here. What we're going to do is we're going to split this up into two possibilities. So, or in a way, two possibilities with two different polynomials. So, if we look at x minus 4, we're going to have x minus 4 plus something. We're going to have x minus 4 minus something. And what is that minus going to be? It's going to be root 9, root 9. And this is going to be very similar to what we just did. And we're going to end up getting y x minus 1 times x minus 7. Of course, I accidentally switched two polynomials around, but because this is a product and it's multiplication, it doesn't really matter what order this is going to be in. So, instead of solving the roots along with to convert to factorized form, because sometimes we won't even know we don't even get a question to ask us x-intercepts. We're just going to simply rub all this out and just use this step here. And of course the x-intercepts from the roots are going to be 1, 0, and of course the coordinates, and 7, 0. So for this here, this is A and this is B. Just though, look at how much time we can save with this new method in A, instead of going through the long process of needing to solve for the roots to end up getting back to our factorized form. Now let's move on to C. And for C, the x position of the vertex is going to be halfway between the x-intercept. So the x coordinate of the vertex is always going to be halfway between the x coordinates of the x-intercept, so 1 and 7. So in this case, just by looking at it halfway, 1 plus 7 is going to be equal to 8. Halfway divided by 2 is going to give us 4 for the x position, which, if we look at the vertex form, is also going to be 4. And for that, I'm going to leave you now, and I'm going to see you next time where we're going to do some more maths or physics. See ya!